And welcome again. There is yet another problem at the screen. It is visible to you, I guess it is visible. And this is a big problem, I guess. Electromagnetic gun. I should have written it missiles, but it's a gun. A long solenoid, this is the solenoid of radius r, its radius is r, produces a uniform magnetic field B naught along its axis O, passing through a straight tube AM. Here it is your AM, this one. This is the tube AM here. Made of dielectrics, is fixed in a plane, well fixed, and made of a dielectric, that means it is non-conducting. So something conducting should be put inside it, and it is fixed. That is also good that it is fixed in a plane perpendicular to the axis at a distance r0 from it. The angle AOM equals alpha. This angle is alpha and equal to pi by 3. So it is 60 degree. The tube is much shorter than the solenoid. Yes, its length is given in terms of alpha and r0. So and the solenoid is solenoid's length is infinity. So that means it is much shorter, no doubt at all. A small sphere of mass m, here, which carries a positive charge q, this is here, is placed inside the tube. Determine the sphere's velocity. This is the barrel of the gun. Determine the sphere velocity at the moment of departure from the tube. Okay, where? Here. Consider the following cases. There are two problems. Problem 1 is and second one is 9. No, it must have been 2. The problem, the part 1 of the problem is the magnetic field quickly vanishes. So it's decreasing. So the sphere travels a distance much less than r0. Why not from here? Much less than r0 during this time. So quickly vanishes. That means you have to find the velocity here at this moment. The magnetic field decreases at a constant rate. dV by dt equals minus k. Minus k. dV by dt is negative. K is not negative. Don't make an impression here. dV by dt is negative, it is equal to minus k. That means magnetic field is decreasing at a constant rate during the time of a sphere motion inside the tube. मतलब अब की बार यहाँ कहीं पर बाहर निकलना है, ये पूरा लेंथ कवर करके बाहर निकलना है अब की बार. How? The friction, perhaps I must be sleeping. The friction and electromagnetic force exerted by the tube of the sphere are negligible. Electromagnetic force exerted by the tube, so इन दोनों के बीच के interaction को neglect करना है. Dielectric है. Something is side here. So, okay, no problem. So we have to solve this problem. And this is the problem. So, in the first case, we barely need this picture. So what can I do? I'm going to make the whiteboard clear. And, well, I can draw a picture here, the circular region. in which this was the center and its radius was r, and it was producing a magnetic field perpendicular to the plane of one of the loops of this solenoid, and its value was B naught initially, and this distance was r naught, and inside a tube a sphere of mass m and charge q was placed, and the magnetic field decreases very quickly, B naught to 0 in no time. So if it is decreasing, that means magnetic field is decreasing, that means the flux that is passing through this region will decrease. Well, it will decrease in no time, but it will decrease. So it will decrease, okay? So the loop will give rise to an EMF. The primary objective of that induced EMF is to produce a current that can support this magnetic field. This side magnetic field is decreasing. So an electric field will produce in this manner here outside the region. You must have known this. The nature of induced electric field inside this and outside this electric field is vortex, that means it's non-conservative, you know all of these things. And so this electric field will be produced here like this, and it will exert a force on this charged particle Q, and this will provide an impulse that will result in change in momentum, and the problem is solved. If you want the mathematics, I can do this for you. This electric field, try to find this electric field. Write E dot dl, the induced EMF is written in this term. Since it will get induced within a loop, so I have put a circular sign here to introduce, to know them, to let them know that I'm going to calculate this integration on a closed loop of radius r naught, and that will be equal to rate of change of flux. And I know the initial flux and I know the final flux, so I'm going to write something like this. This E dot dl will be simply E 2 pi r naught. This is the radius, and that will be minus d phi by dt, okay? So what we got from here? We got the magnitude of electric field equals minus 1 by 2 pi r naught d phi upon dt, and it is going to produce a force that will be equal to QE. So this QE can be written as minus Q by 2 pi r naught d phi by dt, and this force is going to produce an impulse for a very small time interval dt, so that we can write the impulse momentum theorem F dt equals m dv. Its mass will remain constant, and dv is the change in velocity during time interval dt. So f dt, I have to write f dt equals minus q upon 2 pi r naught f dt d phi. Dt gets cancelled out, equals m dv. And being a mathematics student, you know what to do next. B was initially 0 and final velocity will become something v or v1, anything. Final flux is going to be 0 and initial flux was what? Flux is passing through this zone. So flux is B naught multiplied by the area of pi small r square. So this minus q upon 2 pi r naught will be minus B naught pi r square equals mv. Minus sign gets cancelled out and you can easily find the velocity v it will get. So the first part of the problem is being solved. Now we have the second part of this problem as well. So the second part of the problem was yes, thing here. Oh, wait. This thing here moving, suppose that this sphere is moving along this. Oh, a sphere. Okay, sphere thing. Okay. The sphere thing was here. Why is it moving along this axis? Let's take this x-axis and it will, I don't know, finally came at an angle alpha that was given in the problem, and you can see the problem. So I'm going to consider some intermediate condition where when this angle is beta. And the magnetic field, it must not be B naught because it was B naught at initial moment and it is continuously decreasing at a constant rate. And its radius is r. And the magnetic field was like this. So it will create an electric field like this. Just take this total length r at an arbitrary position, and this length is r naught, of course, I know that. So the electric field will be like this. This angle is beta, vertical line and this line, and these two are perpendicular, and this is horizontal line. So this angle will also be equal to beta, and this angle will be 90 minus beta. Okay. And it will have a velocity v here. The sphere is here and it has a velocity v. And it can describe an angle d beta in time interval dt, and it will travel a distance v dt in a time interval dt. So what will be the value of E here? what will be the value of E here? Simply we can write E dot dl for this whole loop equal to rate of change of flux. But this time we don't have any information about flux. We have information about the rate of change of magnetic field. So I want to find the magnitude of electric field, so I'm going to leave it minus sign. I will just get, because I have provided the direction to the electric field. So if I get the magnitude of this electric field, I don't need to consider that minus sign. So the flux will be dV by dt multiplied by this area, because flux is only present, magnetic field is only present in this region. So pi r square. Oh. So now this left hand side will be written as electric field multiplied by 2 pi r is its radius. So whole length of circumference will be 2 pi r, and that will be dV by dt was minus k. So take out of the modulus and write down here k pi r square, not k r square. So k pi r square. And now what? Pi gets cancelled out, and we got electric field equals kr square upon 2r. Well, this is a good result, because it is going to produce a force that will be QE, but this QE is not going to provide the force needed to get the momentum to this sphere along the x-axis. Its component will, and this component along the x component of the force is going to be here F cos beta. So I'm going to write the impulse momentum theorem like F cos beta equals F cos beta dt. We'll write dt. This is just F cos beta is just the force component. We need to multiply by the small time interval dt in which we are talking about, and this will be m dv, and then F equals QE. So Q and E is kr square upon 2r cos beta dt equals m dv. Of course, I'm not going to do the integration, because in this case beta is also changing with time. So I need to make some adjustments. What should I do? I have dt and dv both. dt and dv, not v, that is dv. That's a problem. I wish to use this triangle. This triangle name is O, and the name of this point the C, and name of this point is D. I avoided B because B is magnetic field. C, D. Okay. So I am going to use the sine formula in triangle OCD. How can I do this? I'm going to do this, and how can I do this? These are two different problems. But we have to do this. This is the triangle OCD, and this length is VDT. So I can write one thing, VDT upon d beta. The opposite angle is d beta is equal to, this length is R divided by this angle, and this angle and this angle are so same because the difference, this angle is beta and this is d beta, so they should always be considered parallel to each other. So this is this angle is 90 minus beta, so I can write here sine 90 minus beta. I got what? I got something, V cos beta dt by R, V cos beta, no son. Oh yes, V cos beta, sine 90 minus beta is cos beta, so V cos beta dt by R equals so I need V, I don't need V here, so I'm going to need it d beta by R, cos b theta by R we need. Oh, we have this relation. Can you remember it for a while? So that I can make my calculation. Here is what? Cos beta dt by R. And this is what? dB by B. Here I made a mistake here. This should be dV upon B. Okay. So got it. Q.
Welcome again.
K is not 1 by 4
disturbance.
epsilon naught. K is something some
You
constant.
can write here cos beta dt
Welcome
upon R equals
again after the disturbance.
d beta.
I can write here cos beta
That
dt
is m
upon
beta.
R equals
Just
d beta
place B on the right hand side of the equation.
that is m b dv.
I have
I
something.
just place
Now,
B on the right hand side of the equation.
everything is fine, and I can write q k r square upon t. You
Now
can integrate this d beta.
everything is fine, and I can write
dv
q
as
k
well.
r square upon
Initial
t.
velocity was 0.
I can integrate this d beta
Final velocity is what we are looking for.
and b dv
And
as well.
initial velocity
Initial
beta
velocity was
was of course 0.
Final velocity is what we are looking for, and initial velocity
The
beta
is
was
this
of
angle, so
course
initially
0.
the ball was here. So beta was 0 initially.
Look, beta is this angle, so
And
initially the
finally
ball
beta
was here.
was pi by 3
So
perhaps.
beta was 0
Pi by 3.
initially.
It is given in the problem. And we can find the value
Finally
of beta
beta
again.
was pi by
And the
3
problem has
perhaps.
been solved.
Pi by 3. It is given in the problem.
But no problem is solved.
And we can find the value of
Thank
b
you
again.
very much.
And the problem is being solved. But no problem is solved. Thank you very much.